Honor chair of the corrosion and fouling session, dear experts in heat exchanger technology. When I came closer to the issue of fouling a couple of years ago, I was surprised that there is not really a good solution for fouling protection inside of heat exchanger tubes. And seeing that we have at our own university a new plasma coating technology, which is suitable to coat large-scale parts with diamond-like carbon, I and my colleagues we stood up to tackle the issue of producing heat exchanger tubes which are protected against fouling inside once again. And to tell you this story, DLC for piping, and to give you an insight how far we have come so far and what are today's topics of improvement, further improvement. This is what is it about. My name is Albert Angerbauer. I'm from the University of Applied Sciences in Wels, Upper Austria. This is, if you think about Salzburg and Vienna, if you make a line, then we are in the middle. So this is where we are. Let's jump into the technical matters. So the agenda is to give you an impression of DLC, diamond-like carbon. Then very important is that we discuss the process, and then some fouling tests, then our concept of fouling prevention, then a broad heat exchanger example, welding tests, and then, of course, the promising fields of application, where we see then the whole picture. So the basis of the coating which can be produced with the plasma-assisted chemical vapor deposition process. We come from night reading. This is important. So we are able to first, in the first step, make a hardening of the base material if this is required. Then the compound layer, which makes the sticking of the layer better to the base material, and then the actual DLC layer. We can produce 100 microns. We are stable at 70 in today's, but for fouling it would be enough, maybe 5. So this is the coating thickness which we think is enough, and we don't need really the compound layer and the night reading in these steps. So the properties of DLC. Very important is low coefficient of friction. This is the principle of anti-fouling mechanism. And we have very good wear resistance. So think we have on the market already some sort of layers of coatings inside of tubes, but they are they have not really a wear resistance, so they are put off very soon by abrasives. And this is the mechanism where we think we can stand. Also the severe cases, maybe we need a thicker layer if abrasion is really severe, but we will see. corrosion protection is a property of the layer, but in this field of application, we would say if corrosion protection, the base material has to bring it in full scale, and the additional corrosion protection of the layers only a benefit, but not the basis. Maybe we come to the base materials. Here we can use every steel grades. We have some conductivity of electricity. This is important. Yes, basically for today, I would say steel grades, we can use everyone. So the very important, the reactor itself. We use the RUBIG technology. Then this is a vacuum chamber. We can put the vacuum chamber by a crane out. Then we have an area of 1.5 meter in diameter and 2.3 meter in height. This is the big room where the coating can be done. I would not have tackled the technology if it would not be scalable up to at least 6 meter. So this is what the technology is capable of. We can scale it up. We have in operation a 6 meter high net reading, plasma net reading facility of this type, which could be then upgraded also for DLC coating. So you see, we have really the potential to fully satisfy the needs of the heat exchanger industry. Here, this is very notable. The operation temperatures inside the apparatus is about 500 degrees Celsius, and therefore I'm really I'm really yes, it was not possible to come to Rotterdam, and so I would have taken the opportunity to discuss with the experts of the steel exhibition. What is about the duplex steels? Can we find types of duplex steels which we can coat with such a high temperature and such things? But basically, all standard types of stainless steel can be operated and have not really disadvantages. Why is this process so interesting? We are using rough vacuum and not fine vacuum. The other processes are using 5 Pascal, and here we have this range, and meaning there are much more atoms in the atmosphere, and so the power of the plasma is really, really big. So this is the smaller type reactor which we have at the university. So you see here the cathode. You have to put on the parts on this plate and to connect it, that you have an electrical flow. First trials, I will very short go into this. We had at the sewage plant where they had real severe sewage problems. At the sludge pumping station, we had a test pipe 300 millimeters long, 100 millimeter in diameter. So the results after 1 month without coating, scaling. With DLC coating, no scaling. Just some sand here on the photo. Then we made for 5 months, we had in between purgings with citric acid. So, but the purgings didn't hinder that this that the fouling accelerated with the uncoated tube, and finally there was a 15 millimeter layer found, and with DLC we have no fouling found. So the finding is these purgings were enough to clean again the DLC coating. So we had the inhibition period, which is before fouling occurs. It's always be refreshed by the purgings, and this is how a good operation with DLC coated pipes could work. That we find the time of the longer inhibition period, and then make the cleaning at this point, which should be much longer as without coating, and then you have always very clean situations and ideal heat transfer. So the status I've spoken about, maybe at this point is of importance, the dopings of the DLC coating. Please note, DLC is a wide range and universe of coating possible, but we will focus on silicium doped types and of the standard DLC with hydrogen. So in plate, there is DLC already applied, but plate heat exchangers is really a different story. We will go for the tube and shell heat exchangers. So there's nothing new. The basis of our research is, maybe if you want, the studying the researches of the Technical University of Braunschweig and the Fraunhofer Institute nearby, also Braunschweig. They produced the DLC coatings, but with a fine vacuum. So this is a different process. They have lower temperatures, but then maybe a different plasma type, and so this result ended not really in a marketable product. There was still a wide way to go to find then a tube which is really coated inside. Our approach was then different to that of the Braunschweig institutes. We take a strip of steel, form it to a tube with a gap. And you see this tube with a gap, you can use a standard tube and make the gap inside again. So this is what the industrial way would be for the time. Then we coat this tube with the gap inside and outside with DLC. And then we do the welding and have a coated tube with inside DLC coated again. The question was, how big has the gap to be? So you see here the test setup. The tube here inside with the gap closed at the top and the bottom. The gaps we tested at 10 millimeter down to 0.75, and we saw that the limit was 1.25 millimeter, where we had full sufficient coating inside, and also the silicon content was absolutely in the specification. So look here at the results. You see here a very thin gap in comparison to the other measures. So you can imagine the final forming before welding. It's simply not very difficult. It's in the elastic range of the material. We have not really to form it, and it will be a tube in the roundness which is required. The area where we had satisfying results here in this range. With bigger gaps, it makes not really a sense to our meaning, so we should go as narrow as possible. So the example on tube and shell heat exchangers is we thought maybe 5 meter long and some 600 millimeter in diameter, and the outcome would be that the tubes inside would have been welded together from 2 meter and 1 meter pieces. So we would have tubes with a round seam inside. We made welding tests on the base plates. We had the variant 1, you see here. We were wondering, is there an infringement here on this area? And with variant 2, we looked here. And we saw variant 1, yes, we have a burning off of the layer in this range. And with variant 2, we have very minimum putting off of the layer. With circumferential seams, the welding itself was quite easy. There were no problems reported. And also, if you look here, it's quite fine. But we saw then when we applied pickling that the infringed area is bigger as it seemed in before. So this area would be an area where we could see some fouling. So then I come to the final page, the promising fields of application. Inside coating of tubes, this is where we will focus our research efforts. This is the most exciting area where really the community has no solution available. Outside coating of tubes is maybe already done. We have, you have seen, we can do it. We simply put in the tubes into the reactor. We can do 2 meter, and as I have mentioned, we have the option to go up to 6 meter. This is simply if we get an investor that is willing to contribute to the upgrade of the existing night treating facility, then we could make 6 meter DLC coating right off. Then texture tubes, here I'm thinking of thin tubes. I would say it's also the same as here, simply trying. We don't know the real limits. We cannot calculate for the benefit it would have, but it has certainly a benefit in cleaning. Condenser tubes would be interesting. We have ideas to make new coatings, to make a droplet condensing, but we have been warned that this is a tricky field, and so maybe we make not this in the first place. Then to coat full heat exchangers would be nice, but this is already too dense, the tubes, so we cannot make this really working. We have to go this way at BO1, BO2. I think will not work. We have too many tubes, too small the gaps for plasma operation. Other thing is electric process heaters. They have normally not so many tubes and wider spacing. It depends on the application, of course, but there are standard applications which could be interesting. So then for the summary, I have 2 messages to the audience. First, we are looking for closer cooperation with a tube supplier for heat exchangers who are bringing forward the research, and this company or organization should have own laser welding capabilities. We think laser welding will be an interesting option. And the second is we are looking for cooperation with operators of heat exchangers that are interested to put this type of tubes into their operation and to also go for research efforts to bring this technology forward. So I thank you for your kind interest of this topic, and I wish you a very fruitful conference and exhibition in Rotterdam. Bye.